Today we're going to be talking a little bit more about our unit of filling and wrapping. We're going to be considering some three-dimensional figures again. My name is Ruth Ann Duncan. I'm a teacher of grades 7 and 8 mathematics. Our school is National City Middle School, located between San Diego and the Mexican border. If I wanted to compute the volume of a rectangular prism, what three dimensions would I have to take into consideration, Francisco?
The length, the width, and the height.
Length, width, and height. Everybody agree? Mm-hmm. Yes. All right. So I would have to find three factors that would have a product here of 24. Let's generate some.
12 times 2 times 1. 2 times 3 times 4. 6 times 2 times 2.
What's the way that I could generate an infinite list? Michael?
Use decimals.
I could go to decimals or fractions, couldn't I? And then, if I moved away from these whole number values, I would have an infinite number of combinations that I might think of, at least infinite for our purposes. We've talked about volume of a rectangular prism. Let's quickly change gears for just a moment. How can I find out what the volume of a cylinder is? What am I moving through space? What am I moving through space? Everybody. I'm generating a circle through space. Yes. All right. Now, let's think of that for a moment. If I'm moving a circle through, I heard someone say the word, the third dimension here would be, or that dimension would be considered to be height here. So if I were thinking of the volume of a cylinder, then I've got a height factor here, and then I've got this circle to consider. My base is a circle. What's the area of this base, this circular base? Who can think of the formula name?
The radius.
Radius is involved. What's the rest of it? What's the rest? Radius squared.
Radius squared.
We're missing one element. What is it, everybody? Pi r squared h. All right, there we go. Okay, so we have a circle, pi r squared, huh? And we're moving it through height, and that generates some cylinder. Okay, now we got the language. It's generating a cylinder as it cuts through that space. I'm going to be giving each person in your group one sheet of typing paper, and the task is simply this today. I would like you to design, each of you, the largest possible container closed that you can out of this sheet of paper. What elements might we think about if we were to make the largest container?
The volume.
The volume comes to mind. What else comes to mind?
The surface area.
The surface area. All right. So certainly we're going to be taking a look at some volume and surface area. The objective of today's lesson was to see how far the students could carry the idea of maximizing either surface area or volume. We have been talking about three-dimensional objects for a long period of time, and this finally was an activity that they worked on somewhat independently.
So what are you going to do, the cylinder or the rectangle prism?
I'm going to cut it right here, this side, because the diameter is 3.5.
She asked me how am I going to find the surface area. That was a good question. Because I don't know. I have no idea.
Ow.
Oh, what's half of 11? 5 and a half. Never mind. Dude. 3.
You gotta find the length and the width, and then you find the area of the circle, and then you add it all together for the surface area.
Thanks for the explanation.
You're welcome.
I still don't get it.
As I walked around the class, I observed the dynamic that existed in each of the groups. What immediately occurred to me is that all of the students were engaged in the problem. I also noticed an element of creativity, and that is that the students did not limit their exploration to one single form. And they were discussing the formulas. These things have come alive for them. They take on some meaning.
She told us to make a rectangle.
It's a cylinder.
She didn't.
It's a cylinder.
We can do anyone.
No, she said container. It don't have to be a cylinder.
It's easier if you have a big problem or a hard problem if you're doing it hands-on than if you're looking at it like out of a book and you're reading about how someone else did it. This way you actually get to do it. So like it helps you to find easier ways and you could be more creative.
Cut off the edges and then tape it.
Here's my pen. Put it upside down where you can trace it with the pencil.
I tried that, but they're not starting.
They won't stand.
That's how I got this.
Okay, folks, you need to listen for just a second. Regardless of where you are in your own original attempts, you need to make a group decision. Go with the box that is largest of the ones completed. Try to compute in the next few minutes the surface area and volume of at least the one you're selecting. Recorder needs to record on the transparency for your group. Come up and get a overhead pen and a transparency. You want to compute the volume of this? What formula are we going to use? Pi
R squared, pi r radius squared.
Phi radius squared times the height. Okay, so you need to know the radius. You've got that, and you've got the height. And that will give you the volume, right? But now you're concerned about the surface area. You know what? If I were having a problem and I didn't know the formula so well, I could unroll this, but that might mess it up. I think I can do it more conveniently by roll, 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 roll. Hey, easy.
And we just measure it with the ruler.
Well, yeah, you could just mark it off and then count it off. If you just want to use intuition, how do you think it looks intuitively? Do you think it looks like it holds as much as that or that? What do you think? What do the rest of you think?
Looks like a car.
Okay, why don't you write down then, Anna, that you took a risk and you made a unique shape, an unusual shape, but it looks like it's big on surface area, doesn't it? It's not volume. Would you go for that agreement?
One of our group members, Michael, he came up with the shape and it turned out to be like a three-dimensional trapezoid. And to find the volume, we had to cut off the sides of the trapezoid. And when you put those two sides together, they turned into a square. And so we just put the square and the triangle and the rectangle together. And it came into a really long rectangle. And then we did the length times the width and so on so we can find the volume and surface area.
We're going to move forward now, and wherever you are in recording your presentation, that's all right. The presenter can talk us through. What we'd like to look at is your selection of the largest container or also the most unique.
Okay. First we were just trying to make a shape that could probably make up a lot of volume. And then I just came up with that. It's probably not the one that has the largest volume, but it's different. And I figured out the volume, which is 448, I think. 448 cubic centimeters. And by doing that, I cut this piece off, and then I put it would fit right over here, so I got the volume by using it as a rectangular prism.
Their shape was problematic in the beginning, and they didn't know how to find the volume. So by recognizing the fact that a square can be cut into two triangles, that was their reasoning. Slid that over. Michael, show your shape from the side. What is that shape on the side? This group actually knew. Jennifer?
Trapezoid?
This had two trapezoidal sides. And so they cope with that very nicely, in my estimation. I'm not sure if that's the biggest, but it's unique. Okay. You want to talk about yours a little bit? What were the dimensions?
The volume was 792.
There are several reasons why presentations are appropriate in a math classroom. In my class, I have largely second language speakers, and yet when they come forward to explain the mathematics, explain their thinking, to show what they know, they can do that. They're speaking a third language. They're speaking mathematics.
First, we measured the side right here, how tall it was, and it was first we found out the surface area, and it was 28 inches, 24 inches.
24 square inches?
Yeah, we just cut an inch tall, and then we folded it in, and we got a rectangle.
At the end of the day, I can go home and say to myself, you haven't just taught a select few students. You have taught everyone in your class. Certainly, this is the great turnabout for me after 25 years of teaching to say this to myself, that mathematics is for all students. All students are learners. All are naturally gifted. And I've capitalized on that. And that energizes me and keeps me here and happy.
When should you intervene to help students correct computational errors? How could you restructure this lesson for your students? Discuss Ms. Duncan's contention that mathematics is for all students.